Alright everyone, so today we're going to be doing 6.9, which is going to be operations with radical expressions. So our key concepts and main ideas today are that a radical expression is in simplified form when the following conditions are met. The radicand has been factored completely with all perfect factors removed. The radicand contains no fraction, and no radical appears in the denominator. So we learned about the first one yesterday. Now we're going to add in some operations that we can do on the radicals. So you can only add or subtract radicals if everything under the radical is exactly the same, the radicals are of the same index, so like a square root, a cube root, a fourth root, and if there are any variables present outside the radical, that they are the same variable to the same power. So as you can see in the green, that's the only example that allows you to combine like terms. Okay, all the ones in the red, you can't do that. So we're going to look at an example of each of these types so we can test it out. Or many different types, not necessarily all of these. I'm just going to do 1 and 3 first because they're on this side, and then we'll do 2 and 4. So we look at number 1, and I see that they have the same radical, same index, same radicand. Now outside of this, are there any variables present here? Any variables outside the radical in this question?
No.
No. So now we can just combine like terms on the outside. What is 3 minus 2?
1.
So the answer is 1 radical 5x, which is really just what?
5x.
Yeah, radical 5x. And that's your final answer. Now down here on number 3, bless you, you're going to notice that these are not the same radical, but we can try to simplify them so that they are, and then see if they can be combined. So what can I break up 12 into?
3 and 4.
3 and 4.
Yep, 3 and 4, or 6 and 2. Either one's going to get you the same result. And then 6 breaks up into?
3 and 2.
Now I circle all my primes. And now if I'm square rooting, I'm looking for a pair of 2. That pair gets to leave the radical. And behind stays the 3 and the x. And since the x is to the first power, it can't be divisible by its index, so we just leave it inside. Now for this one here, what can the 75 be broken up into? 15. Good.
3 and 25.
Or 3 and 25, that would have worked too. What does 15 break up into?
5.
3 and 5. I'm actually going to put them in the opposite position. You're going to see why.
So you can pair them up together.
Yeah, I could have still done it, but just so everybody can see it better. So these are the 5s that are paired. So it's going to be plus 5 radical 3x. Everyone with me on how we got that? And then this one can't be simplified, so I'm just going to bring it down. And I'm going to rewrite it as minus 1 3x, radical 3x. Now I'm just going to combine the coefficients. So what's 2 plus 5 minus 1?
4 would be 6.
6, and then you keep that same radical they have in common. And that's the final answer. Make sense so far? Okay. Now we're going to go ahead and do number 2. What do you notice about both of these radicals here?
This cube.
It's cubed, good. So, is there any variable outside the radical here?
No.
No.
No, so we're just going to combine like terms. So 12 plus 8 is
20.
20. And then this one, we have the same radical, but what's wrong with the outside?
Variables.
Variables. But the variables are the same. What's the problem?
Second powers.
Second power. The powers of the variables. You
Good.
can't combine an x squared with an x.
Exactly, they're not like terms. So just like you wouldn't combine 6x and 6 and 4x squared, you can't add these either. Now, this you would just say cannot be combined. You would just say there's nothing you could do. But I just want to bring up something, because I see this come up. They could ask you, give me this answer in factored simplest radical form. They could factor out a GCF here of 2x radical 5, right? that would leave me with 3 plus 2x, wouldn't it? So they took out a GCF. So they can take out a GCF as well. So I'm not saying you had to do that here, but I just want to point out that they could have you take out a GCF. So that's what that would look like. You can take out a radical GCF. Any questions about that? Let me know when you're ready. Alright, moving on. Now we're going to do some multiplying radical expressions. So, yes, you can actually multiply radicals with different roots, like if it's a third root or a square root, but today we're only going to focus on when the roots are the same, because that's a whole other procedure. So when they are the same root, all you have to do is multiply everything underneath the root and put it under one big root. So everyone see how I got that? -8 is a perfect cube root. Anyone know what it is?
2.
Not 2, but
Negative 2.
Negative 2.
yeah. And then what is the third root of x to the third?
Oh, that's just X.
Just x, because you divide it by its index. And that's the final answer. Now on number 6, we have to use the distributive property. That gives me radical 81x, oops, that one was like, I don't know what it's doing.
How long was that?
Yeah. 81x squared plus 5 radical 3x. What is the square root of 81?
9.
What is the square root of x squared?
X.
This can't simplify, so we just bring it down. And that's our final answer. Any questions about that?
I have a question.
Sure.
So if you're multiplying it, why do you not combine the plus 5 with the radical 3x?
Good question. So this is what we call a mixed radical expression. This is a regular number. This one's inside the radical. So only regular numbers can be multiplied with the regular numbers, and then anything inside a radical can be multiplied with other things inside radicals. But if one's inside a radical, one's not, you just put them next to each other, which implies the process of multiplication between them, but you can't do anything with it. Yes?
You're square rooting and then you're squaring something. I thought they always cancel each other out.
Yes, they do cancel each other out.
Then how do you get 9x?
It's 9x without a radical. She canceled out the radical.
This part right here, 81, what's the square root of 81? 9. And then what we did was we did essentially cancel out the square root, didn't we? This canceled this out, leaving me with just the x.
If it was without a square root, it would have been the same thing, but it has one, so it's just 9x.
Now, there's one last thing we have to do about this. We took an even index root and we got an odd result. So what do I need to put around that x?
Oh, you need to put an absolute value.
Yes. That's a very forgotten.
Just the x?
Just the x. The 9 numbers are fine. It's just the variables you have to worry about. So keep in mind, commonly on like an SAT or ACT, instead of doing the absolute value, they might just say at the top of the question, this only works for values of x that are greater than 0. So instead of like saying you can plug anything in, they'll just specify. So that's a way to get around putting the absolute value. I'm not suggesting you guys do it, but I just want to mention that so that you're aware that that's how they usually deal with it. Alright, so this is one of those questions that you can solve different ways and get the same result. So here's the way that I would go through it if I were just seeing this question and I want to solve it. I would see the fact that before I simplify anything, I see I have a 16 here, and I'm taking the fourth root of it. What is the fourth root of 16?
2.
2. And then I know we can simplify the variables, but I'm going to leave them inside for now. You're going to see why. Okay? So everyone with me on what I just did.
Oh, so you can... Have we been simplifying before we're doing the operation the whole time?
Sometimes, but oftentimes it can't be, so we just got lucky with this one.
Got it. Okay, great.
So this always has an implied 1 in the front, so we can multiply the numbers by each other. So the 1 times the 2, which is 2. And then anything under the fourth root, I can just put under one big fourth root. So I have the 15 from this one. And then what is x to the 5th times x to the 3rd?
X to the 8th.
Good. You remember you add the exponents when you're multiplying. And then it's going to be y to the 12th. Now, the fourth root of 15, we can't simplify. It would break down into 3 and 5, neither of which can be paired up. But what is the fourth root of x to the 8th?
X to the 2nd.
X to the 2nd. If you forgot, you take this number, divide it by this number. If it goes in evenly, no remainders are left inside the root. What is 12 divided by 4? Yes. And then inside the radical, we have a 15, and that's it. We didn't have anything else left, so we don't need such a big root. That was just. But we did take an even index root, and we received an odd variable. So what do we have to do?
You gotta go around the y.
Just the y. Any questions on that? This is truly one of those concepts that is very much like the more you practice, the better you get at it. Okay, this one we're going to use our old friend FOIL. Remember FOIL? First times first. Outer times outer. Now when you multiply a number and a mixed radical expression, you just multiply the number by the outside part and then leave the radical. Same thing we're going to do for these two. It's going to be 10 radical 2. And then for the last one, when you multiply two mixed radical expressions, you multiply the outside numbers together and then the inside numbers together as they are under the root like that. So does anybody have any questions on how we got those 4 terms before we proceed? Okay. So what do you notice about the middle 2 terms?
They can be added together.
Good, they can be added. And then this one can be simplified, because what is the square root of 4?
2.
2. What operation is existing between these two? Good. So simplified 4 is, radical 4 is 2. What's 2 times 8?
16.
Good. So this becomes 16. You see that? Now we have 2 more legs terms to deal with. What's that going to come out to be?
36.
And that's as far as you can go, because you treat radicals like variables when they can't be simplified. We can't add 2 terms that are not like terms. Now there's nothing wrong with question 9. We're just going to skip it for the sake of time to address everything. So you can try it on your own if you want more extra practice for whatever reason, but we're just going to skip it just because we want to save some time. So I need to address this important concept. These 2 expressions are what we call conjugates. Anyone remember what a conjugate is?
Oh my god, no.
Something it can be
It sounds familiar.
So a conjugate is when we have 2 binomials.
It's like a reverse, so 6 plus x would be 6 minus x.
Yes. So see how these are identical binomials except for the fact that the term between them, or the operand between them, is a different sign, opposite of each other? Everyone see that? So conjugates have a special characteristic about them, and you're going to see that here. So what we're going to do is we're going to FOIL this. So we have the square root of x times the square root of x. Now here's another thing that's important. When you multiply 2 identical square roots together, it just becomes whatever's on the inside of them, which is x. Outer minus 2 radical x. Inner is plus 2x, or do square root of x. And then last is 2 times negative 2, which is?
Negative 4.
Yes. What do you notice is going to happen with those 2 middle
It's
terms?
going to cancel out. It's going to be x minus 4.
Yes, they're going to cancel out, which just leaves me with x minus 4. That is a characteristic of conjugates. That's not a coincidence. That will always happen with conjugates. Those 2 middle terms are going to cancel out. But remember, we took a square root and we received an odd index. We took an even index square root and we got an odd power, sorry. So this has to have an absolute value on it. Any questions about that? Okay. On. Now we're going to do some dividing radical problems. So when you divide radicals, at least for now, you want to make sure they have the same index. These both have an index of 2, the square roots. So you can just make them into one big radical, like this, okay? And now we're going to simplify that. What is 18 divided by 2?
9.
Good. And what's x to the 5th divided by x to the 3rd?
X to the 2nd.
Good. And if anybody forgot how to do that, if you're dividing with a common base, subtract numerator minus denominator, okay? What is the square root of 9?
3.
Square root of x squared?
X.
That's your final answer. But almost. What do we got to do?
Absolute value.
Because this was even and this is odd. Now here's the one that is a little bit tricky sometimes. Domain restriction. You might be thinking, there is no domain restriction on my final answer. There's no denominator to worry about. There's no square root. But here's where it comes into play. Had this x originally been 0, that would have been 2 times 0, which is 0, and the square root of 0 is 0. Could we have divided in that case if the denominator was 0? No, and if you remember back to your stations activity, what did we get for that one that had a 0 denominator? Not 0, but
Undefined.
undefined. So could this answer have even happened if this x had been 0? Could we have even proceeded? No. So the domain restriction here is 0. So even though the final answer doesn't have any restrictions, we couldn't have even gotten to that answer had this been 0. Does that make sense? Okay. We'll try one more like this. So once again, we have a third root on top and bottom. We can combine it into one big root. Which comes out to be 54 y to the 3rd, right? Now I'm going to break this up, 2 and 27. 27 breaks up into 9 and 3, and 9 breaks up into 3 and 3, right? What size grouping are we looking for here?
3s.
3s. We have 3 3s. So those get to leave the radical. And then the 2 had to stay behind. What is the cube root of y to the 3rd?
Y.
And that fully simplifies, no remainder. So that's my final answer. No absolute values required because we took an odd index to begin with. What are my domain restrictions on the y? If y had been what here, we wouldn't have gotten here? 0. Because that would have made my whole denominator 0, and that can't happen. Now I don't care what math class you're in, unless you're in maybe some really, really high math class where they tell you to avoid to exceptionalize this. 0 can't be in your denominator, okay? If you're in calc, if you're in pre-calc, if you're in calc 3, okay? You want to remember that theme throughout all math classes. You get a 0, that's bad. You don't want the 0 in the denominator. So, now we're going to talk about rationalization. Rationalization is a process that allows you to get a radical out of the denominator. So if you're asked to rationalize, or they want your answer in rational form, you need to do this procedure. There's 2 versions of this procedure. We're going to learn about both. The first version is when you have a radical in the denominator, but it's a monomial. So does everybody see why this is a monomial? If you're wondering what a binomial one's going to look like, yeah.
It only has one significant figure.
Yeah, that's true. So in this case, this is what a binomial radical denominator might look like. It could be like 4 minus square root of x, Or it could be like radical 3 minus radical 5. So anything that's more than one term and has a radical in it, more than one or more radical. So we'll talk about that in the next slide. But this one's a monomial. So we're only going to deal with monomial radicals with an index of 2, so square roots. I decided that we're not going to do the third and the fourth because they're a little bit more difficult. So we're going to multiply the top and bottom by whatever your denominator is. Okay? This just becomes 3 radical 2x over, what did I say about when you multiply 2 identical square roots together? Just becomes what's on the inside, right? And what is the domain restriction here?
0.
0. Now once again, you got to be careful not to forget these absolute values, because we had a square root and it became even to odd. And that's how you do it with this monomial. Now with a binomial, we're just jumping to number 16. You have to use what's called the conjugate. I mean, we just talked about the conjugate. What's the conjugate of radical 3 minus radical 5? Yeah, same thing but with a plus sign. So you multiply the top and bottom by that when it's a binomial. You distribute on the top and you get 2 radical 21 plus 2 radical 35. Now, to multiply these two in the denominator, you can use FOIL or you can use the area model. You have the option. Use whatever you want, I don't care. What is radical 3 times radical 3? 3. Radical 3 times radical 5? Radical?
15.
Good. This is negative radical 15, right? And what is radical 5 times radical 5?
Negative radical 15. 25. Oh.
Yeah, radical 25, which is 5. Any questions about those multiplications? Now, what you're going to notice is these are like terms, right? And then these actually cancel out. If you take radical 15 and subtract radical 15, those go away. So what is 3 minus 5? Negative 2. Now, isn't it true that I can divide each of these by the 2 in the denominator? So these cancel out. But that leaves me with a negative 1 in my denominator, right? So that means these all have to become the opposite sign. Now you can't simplify this any further. If you want to try to break it down to see it for yourself, radical 21 breaks up into 3 and 7, and radical 35 breaks up into 5 and 7. None of those have any groupings, so they have to stay as they are. That one's probably the trickiest one we do today, for the most part. So we're going to skip 17 and jump into 18. What's the the regular conjugate of this? X.
Minus.
Good. Minus radical x. Before we go into multiplying, I want to see if you can find any domain restrictions right off the bat here. X can't be 0, that's true. But, even better, what can't we have inside a radical or it becomes imaginary?
Negative.
Negative. So x actually would have to be greater than 0, strictly, right? Now, do I need to write both of these? If x can't be 0 and x has to be greater than 0, are these necessary to write both of them?
No.
No, this one's redundant, right? Does everybody know what I mean by redundant?
Equals that one.
Yeah, so this isn't wrong. It's just redundant, okay? Make sense? Because like saying the same thing again. So if you wrote that on the line and you had both, I wouldn't like mark you wrong, but it's just redundant. So obviously if you multiply anything by 1, it just becomes itself. But in the denominator, we're going to have to use FOIL or area model. X squared, this, and negative x, right? These are not like terms, but these do cancel each other out. And that leaves me with x squared minus x. Yes. Sure. So this is the final answer, but this one actually produces more restrictions on the domain. And I want to show you why. What can I factor out of this denominator? What's the GCF? X, very good. Now here's the problem. We already restricted the 0, but what other number would make this denominator 0 now? 1. So x also can't be 1. So it can sometimes happen. And either of these answers are final acceptable answers, by the way. These are the same meaning, okay? Either one is fine. Sometimes you get additional domain restrictions based on your final answer if your final answer has a denominator that has variables in it. Does that make sense? Okay, so let me stop my